Well, good morning, everybody, and welcome to Wednesday morning at Java 1. It's encouraging to see a good turnout here this morning for a geeky talk on G1GC. I'm Charlie Hunt. I'm the performance architect at Salesforce.com. I'm also the lead author of the Java Performance book. And on stage with me here is Monica Beckwith. Monica is a JVM performance engineer at Oracle. And Monica is largely leading the performance effort related to G1GC. So I think you're going to find out over the next 50 to 60 minutes, you're going to get jammed with a lot of information. And we're going to move pretty quickly. We got a lot of slides here. But I think you're going to enjoy and you're going to find useful what you're going to see. Hopefully you walk away from here with enough information and armed to go back to your offices and be known as the G1GC expert. So the standard safe harbor slide, now that I'm not an Oracle employee, you can believe every word I say. Just kidding, of course. Basically what this thing means to me is if you're making some purchasing decisions, don't make those purchasing decisions based on what you hear today. Okay, enough of that stuff. So the program agenda here, the first part of this, first half of this session, you're going to hear me talk about laying the groundwork for why would we want to use G1 and give you an overview of how this thing works. So we need this background to understand how do we go about evaluating G1 as a GC, which is going to be the second part that Monica's going to cover, and then she's going to move into how do we do this analysis of G1. In other words, how do we take this information that's coming out of the GC logs, figure out what it means, and then if we need to do some tuning, what is that tuning that we need to do? So here's the second part here that Monica will present. So when should we consider G1, or why G1? Well, we're looking for a GC that has a couple of really good attributes. One of those is that it can operate concurrently with application threads, kind of like what we see in CMS. So CMS has old generation collection that operates concurrently. And we'd like to be able to compact free space without these lengthy induced GC pauses. So in CMS, in order to compact that old generation space, we have to go through this painful full GC. So we'd like something that frees us of that sort of issue. We'd also like some more predictable GC pauses, and we'd not like to sacrifice an awful lot of application performance throughput. In addition to that, we'd also not like to have to throw an enormous amount of Java heap at this in order to achieve either our throughput goals or our latency requirements. Okay, so G1 is OpenJDK's low pause, low latency garbage collector. It's intended to be the long place replacement for CMS. It was officially supported in 7 Update 4. They continuously are making improvements and updating to it. So if you start an evaluation of G1, start with the latest update release, because there has been a lot of changes that continually being made. And you're also probably seeing a lot of updates coming recently out of Oracle these days. Don't know if that means they're making a lot of updates to G1, or maybe it's something else. But if you're following the news, you'll get an idea of what that is. Anyway, so G1 is concurrent, so it's got some concurrent phases to it. So refinement, marking, and cleanup, those phases in G1 are concurrent. So in other words, they run in parallel, or I should say at the same time as your application. It's also multi-threaded. In other words, it's parallel. So the stop the world pauses in G1 are multi-threaded. The one piece of G1 that's not multi-threaded is if you get in this edge case where you need to do a full GC, it is currently single-threaded. But it is designed, in a sense, to avoid full GCs. If you're getting to a full GC, you should be doing some tuning. And hopefully that tuning is very minimal. There is an RFE to multi-thread full garbage collections in G1. At this point, it hasn't been implemented because we haven't seen enough evidence, or JVM engineers or Monica hasn't seen enough evidence to justify it. So the general recommendations of today. As of Java 7 Update 6, I wrote this slide about a week ago, and I see we got another update release. So it's actually Update 7. So you should consider using G1. You have a full GC that's either too long in duration or they're occurring too frequently. And this is going to be true for both of whether you're using CMS or whether you're using parallel GC. Now, if you're using CMS today, and you can run your application without experiencing a full GC, I would suggest you to stay with CMS, because your minor GCs or your young GC times will probably be faster today with CMS than they would be with G1. The focus today has been, thus far with G1, has been to reduce or eliminate the need for full GCs. As G1 continues to evolve and the focus starts to shift, you'll see that they will start to address how do we achieve minor GC times that are equivalent or better than what we can see with CMS. Likewise, if you're using parallel GC today, if you're able to avoid full GCs, I would continue to use parallel GC. However, in the future, as G1 continues to evolve, you will expect to see, as I mentioned earlier, G1 will replace CMS. It's also likely that the G1 GC framework will eventually replace the parallel GC. So there will be a parallel GC version or type of implementation that's built on top of the G1 framework. A little bit of dirty laundry here in OpenJDK. There's currently 3 different GC frameworks in HotSpot. Wouldn't it be nice if there was only one? So here you can kind of understand the motivation of why G1 is, and the G1 GC framework is the future for OpenJDK's GC. Okay, so what do we need to know about G1 in order to start our evaluation? So what I'm going to do here over the next several slides is I'm going to do a little comparison with how CMS works and how G1 works. I think most everybody has a sense of how CMS generally works, and we'll see how that contrasts with what G1 does. So everybody's probably familiar with this diagram that's on the left-hand side of the hotspot GCs have this layout of an Eden and 2 survivor spaces and a larger old generation typically. So you have these young generation and old generation. And they're split up, young generation is split up into Eden and survivor spaces. And old generation is generally one larger space. And in the case of CMS, objects are collected in place. There's no compaction that's done unless there's a full GC. Likewise with parallel GC, collections in old generation don't occur unless there's a full GC. Now if we take a look at G1, essentially G1 allocates this huge large area as a Java heap. That is then split up into chunks or regions. And the JVM picks how many regions there's going to be, and it tends to target around 2,000 regions. In reality, what ends up happening is these regions are then mapped to a logical notion of Eden and survivor and old generation. So in this diagram, you can see that there's different colored squares here. So what I've done here is anything that's colored a light green is a region that's logically mapped to an Eden space. Likewise, something that's yellow here is mapped to a survivor space, and blue here mapping to an old generation space. So you still have this notion of an Eden and a survivor and an old generation, and they're just a logical set of regions. And the way that G1 works here is when a collection occurs, what you're doing is you're evacuating or copying / moving objects from a given region into another region. Either you're copying objects from, say, an Eden into a survivor space, or you may be moving them from a survivor space into old generation, or you may be moving them or promoting them into a new unused region. So essentially what you're doing is you're evacuating and releasing this region, and you're saying, okay, this is free to be used for something else. So these regions are designed to be collected in parallel or with or without stopping the application threads. So there's portions of these regions that can be collected while the application's running, and when you're evacuating, you're going to be doing a stop the world pause. So as I mentioned earlier, these regions can be allocated or mapped to an Eden space, a survivor space, an old gen space. One I haven't talked about yet is a humongous region, and an unused one. In other words, it's currently not being used by one of these other areas. So humongous regions are basically set aside and are allocated to hold humongous objects. Now, humongous object is basically something that's an object that's larger than half the region size. And it's a set of contiguous regions. So this is how we deal with very large object allocations that might be larger than, say, a region size. An important point here is collecting humongous regions to this point has not been optimized. So you should be having this aha moment that says, aha, if I got large objects in my application and I'm expecting those to be collected in a timely manner, not a good idea. Okay, so let's see how CMS works and compare that with how GC works in G1. So I've got a diagram here. It's colored now from what we saw earlier. So a light green color here is young generation space, and you can see that's split between the Eden and the two survivor spaces. And then you see a bunch of this blue color in this old generation area. So this would be a snapshot of what CMS might look like as your application's been running for a while. Things have been promoted into old gen, things have been collected, and you see this sort of scattering of objects that are sitting around in this old generation area. So a key thing to understand here again is this deallocation with CMS. In other words, the way objects are collected in old generation is they're deallocated in place. There's no notion of compacting this space together unless you're getting this full GC. Okay, so during a young GC, any of these live objects that are in Eden and survivor space are then copied to the other survivor space, and there may be some objects that are promoted into old generation. So if I move to this next slide, so this would be a snapshot of maybe what this heap looks like after a minor GC or a young GC. So the darker blue color here in old generation were objects that had been promoted, and the darker green here is objects that were still live in the minor, after the minor GC, and they've been copied into the two survivor space. Okay, so let's take a look at how a young GC works in G1. So again, our Java heap is divided into regions, and you can see this designated by the little squares here. So again, the blue colored ones here are old generation regions. The light green ones here are young generation regions. So both the young gen and the old gen are merely a set of regions, as I mentioned earlier, and they're not required to be contiguous. Okay, so I've got a couple of young generation regions here that are circled, and we're going to do a minor GC. So what happens? We take any of these live objects in young generation and we evacuate those to one or more survivor regions, and some of them may get promoted into an old generation region. The other thing that happens is we calculate the size of the Eden size and survivor size that we're going to use on the next GC pause. So one thing that you might be thinking about here is, well, how do we do that? Well, there's some accounting information that we keep for each region, and I'll talk a little bit about that a little bit later. So based on this accounting information, we can get a sense of, based on a pause time target that we've set, we think it's going to take about this much time to do the next minor GC or the next young GC. That's how we determine to figure out how to size the Eden and survivor space. So one thing to think about here, one of these nice attributes of these regions is it's very easy to add regions to a given space, and it's very easy to remove them. So it's very easy to do resizing. So of course, young GCs are a stop the world pause. Okay, so at the end of a young GC, you can see here that I've changed some coloring here. We've evacuated some of these live objects into a survivor space. So this is the dark green area. And we've also had some promotions into an old generation region. So that is the dark blue here. And then the thing that's not really shown here is we don't really have a sense of whether the Eden or survivor sizes have been resized. Couldn't really figure out how to do that in this example. But that's a possibility that could occur. So to summarize that, a young GC in G1, we have this single physical heap that's split into regions. We have this notion of humongous regions to deal with these large objects. We don't have this separate young generation like we saw in CMS. It's also very easy to resize. We could add or remove regions as we need them. Young GCs are multi-threaded. They're a stop the world type of pause. And we evacuate anything that's live into some other regions. Okay, so now we're going to shift to saying, how do we collect old generation? So we're going to take a look at CMS here and refresh ourselves as to how this works in CMS. So the mostly concurrent marking phase in CMS has two stop-the-world pauses in it. And that is the initial mark and then a remark. So just real briefly, in the way that this works is, you reach some heap occupancy of old generation. It kicks off a concurrent marking phase. This is the initial mark, so it does this short little pause. It then goes into this concurrent marking. It goes through old generation, says, okay, this is all of the live stuff. And then it says, okay, what has changed in between now and when I kicked off the initial mark? So this is the remark phase, and it goes back and does that. And that's, again, a stop-the-world pause. So after this marking is done, it goes into this concurrent sweeping phase. And it sweeps over the entire old generation area, and it deallocates in place the unmarked or the dead objects. So at the end of this, so you can see on this slide, I've got a bunch of this stuff that's been marked, and now that this sweeping has been completed, I've freed up a bunch of space. So you can see here that there's no compaction of old generation that's gone on here. So let's take a look at this, how this works in G1. So the concurrent marking phase, there's a one stop-the-world pause, remark, and you would see this in the GC logs as GC remark. The initial mark is actually piggybacked, and what I mean by piggybacked, it's done at the same time as a young GC. And what you would see in the GC logs is you'll see this indication that it's a young GC, and immediately after that you'll see this thing that says initial mark. That tells you that on that young GC, it also did an initial mark at the same time. So there's no separate notion of an initial mark like what you saw in CMS. So during this concurrent marking phase, if we happen to find a region that has no live objects in it, these are denoted here with the large X. So these are regions in old generation we found that there's nothing live in it. At the end of remark, we can reclaim those regions immediately. So the other thing that happens here as we're going through this concurrent marking phase, we do this accounting information to give us an idea of the liveness, and we also get information about who has object references into our region. So that gives us an idea of how long it takes to do a collection of that region. So as I mentioned, at the end of this remark phase, you can see here these two regions that were marked with the red X are now gone. They've been reclaimed. And we know this liveness information, or we have a sense of how costly it's going to be to evacuate or collect another old generation region. So the way that we go about reclaiming old generation regions is we choose the regions that have the lowest liveness. Maybe a better way to say this is those that have the least cost associated with it from a duration of time perspective. And then we collect some of those at the same time as we do the next young GC. So there's no separate notion of a separate pause to do a collection for old generation. We do that at the same time as a minor GC. So what you'll see in the GC logs when this type of event is occurring, rather than saying GC pause young, it's GC pause mixed. So what that mixed means is we're doing a mix of collecting young generation and a portion of old generation. So here I've got identified some young gen and old generation regions that have been identified as candidates to collect. So after this marking has been completed and the next minor GC occurs, next young GC occurs, we get this mixed GC and we've collected both old generation regions and young generations at the same time. So you can see here with the dark blue, this was the amount of stuff that was still live in the old generation regions that we collected. Likewise, the things that are still live in young generation are the dark green. So to summarize this, in G1, the concurrent marking phase gives us this accounting information. It gives us a sense of how much it's going to cost to collect those old generation regions. It identifies those best candidate regions to collect on the next minor GCs. There's no corresponding sweeping phase like we saw in CMS. And the remark algorithm that's used in G1 is different from what we saw in CMS. Remark and initial marks at times could be rather painful from the standpoint of duration of time in CMS. G1 uses this thing called snapshot at the beginning, SATB, and it's a very, very fast remark. I have seen very, very few applications that have a lengthy remark phase. Very, very few. So old generation regions are collected by evacuation pauses. These are stop-the-world pauses because they're being done at the same time as minor GCs. And the ones that are completely empty can be collected at the end of the remark phase. But reality is most reclamation happens in the evacuation pauses. So if we look at the differences between CMS and G1, CMS is very hard to tune. I hate tuning CMS. I don't know about you guys, but you look at a command line option for CMS, this is probably about as small a one as you'll ever see. Contrast that with G1. G1's goal is to require only a min and max heap size and a GC pause time target. You might decide to tune at which heap occupancy you want that concurrent collection to start off. So as an example, you can see there's quite a bit of difference here in the set of command line options that you might use here. I would suggest that if you have a sense of what your GC-induced pause times you're looking for going to be, go ahead and set that and use that as a starting place. And then based on what you're seeing with GC logs, then do the tuning of when you want the concurrent marking to start. One of the key differences here with the heap occupancy of when you want that marking to start is different between CMS and G1. In G1, it's the occupancy of the entire Java heap. In CMS, it was the occupancy of old generation only. So that's one thing to pay attention to. There's some consequences to further fine-tuning young generation or survivor spaces with G1. Essentially what G1 does when you give it a young generation sizing, it basically says to G1, you believe you can do better than G1 can at pause times, or you're basically telling G1, ignore the pause time target because I think I can do better. Likewise, if you do something like setting survivor ratio, it's going to have that same interpretation. Okay. In the area of footprint, if you take CMS or parallel GC with the same Java heap size and you migrate to G1, you can expect to see a slightly larger JVM process size. And that has to do with these accounting data structures, largely related to what's called remembered sets and collection sets. Remembered sets, or R sets for short, track object references into a given region. And there's one of these per region. And what this enables is the parallel and independent collection of a region. And its footprint impact is usually less than 5%. The collection sets, or C sets for short, is the set of regions that are going to be collected on a given GC. So all of the live data in a collection set, in other words, that set of regions that's identified to be collected, is that set of regions that's going to be collected on that GC. Minimal impact here on the footprint size, usually less than 1%. Here is an example G1 GC log. So you can see here some things of young GCs here, the first couple, and here you see on that third line, you see this initial mark that's happening at the same time as that young GC. You can see this concurrent cycle being started. You see that remark, you see the cleanup, and then you see a young GC, and then you see a mixed. So mixed, again, is we're seeing old generation regions being collected with young generation regions. Okay, I'm going to turn it over to Monica, and she can educate us on G1 and give us all the gory details.
Thank you, Charlie. All right. So again, I have a lot of slides, and I'll try not to go fast, but there are some things that we can look at. You will all have the slides, so I've put as much information on these slides as possible. And B, we have some links to a blog by Poonam Bajaj, and what I'm going to cover, some of that information is already on the blog, so I may go fast during that. So how do you evaluate G1? I keep on saying this over and over again. Understand G1 defaults, right? What are the defaults? How they impact your application's behavior? Basically, what default contributes to what behavior? And why are they necessary, first of all? They're necessary to address your goal and set priority. So what are the goals? Throughput, latency, and minimal footprint, right? So for G1, the goal is low latency, right? So these are the defaults. Max pause time target defaults to 200 milliseconds. and the automatic resizing of the young gen is between 20%, which is a minimum, and 80%, which is a maximum of the Java heap. Okay. Okay. Sorry. Understand the defaults again. What happens when you set XMN explicitly on the command line? It meddles with your default, right? G1 does its, remember, G1 has this past time target as its main goal, and it's trying to resize the nursery to achieve that goal. And when you set XMN, which is the nursery max and min equal on the command line, G1 will no longer respect the past time target. It will respect the fixed nursery size that you just set it to. And when the heap is expanded, guess what? You have explicitly set your nursery to a value, and so that will not change when your heap expands or even shrinks. So how do you evaluate G1? You should know your performance requirements. So we often observe folks that want to improve their response time, throughput, and footprint, right? But response time, be careful. Just using average response time is not enough, and I'll talk about that right now. So I know, we all know SLAs have this response time criteria, right? But what is average response time, right? It's basically adding up all your sample set and then dividing by the number of samples, right? So do you think, what happens when you have a significantly varying or different values over a large sample set? Are you capturing them all? Not with average response time, right? So there are other response time metrics that you should consider. Worst case response time, 95th percentile, 99th percentile, 90th percentile. So our recommendation is consider 90th plus percentile. So what does that mean? That only 10% of your response times are worse than that 90th percentile number. So please do that, because imagine, so in a web server, again, only 10% of your people are going to experience worse response times than what your number are. So if you want better, then go with 99th or the worst case, tune like that. So let's say we're targeting low latency. So you should know this flag. Defaults to 200 milliseconds. You want lower or higher, set it on the command line. It provides a hint to G1, to the collector, that you need less than or equal to that many milliseconds, right? And G1 will do its best to meet the past time goal. How will it do that? It'll adjust its Eden and nursery and survivors, Eden and survivors, and the heap size and other related parameters. Charlie spoke about that earlier, to start to stay within that goal. And then check your logs, right? I mean, your logs will talk to you. They will tell you if you're actually meeting your past time goal or not. So I'm going to provide lots of examples on this. So now, what if you want to evaluate G1 for throughput? A, you should know that G1 is low latency, is designed for low latency, right? So it's new to the throughput game. So first, let's define throughput. What is throughput? It's the percentage of time not spent in GC, right? So since G1 is new, guess what? We're saying that we're okay with, so the GC time ratio is the throughput goal, right? It's a log scale. So it defaults to 9 for G1. That equates to a throughput goal of 90%. So you're okay with 90% of application time and 10% of GC time. Imagine the throughput collector that we have, HotSpot's throughput collector, parallel GC. That is 99% throughput goal, 99% application, 1% GC. So there is a starking difference right there. So my number one comment to you is, if you want to evaluate G1 for throughput, relax your past time goals. Aggressive past time goal indicates to G1 that you're willing to sacrifice, or you're willing to sacrifice your throughput because you're willing to bear an increase in GC overhead. So again, how would you do it? How would you tune it for throughput? You would do something similar to what you've done in the past with parallel GC. Use new ratio, new size, max new size, XMN, whatever, to your advantage. Note, again, fixing your young generation size indicates that you're not concerned about meeting a low pass time goal. So again, evaluating G1, replication of production environment is very important. It's important to understand what environment you're working with, what are the issues, fragmentation, spikes in allocation, are you replicating those issues? You need to know the phases and how long those phases run in your production environment. And also the worst case behavior, and how often does the worst case behavior, the frequency or the likelihood of the worst case behavior. You need to understand all that. And make sure that in your benchmarking, you are capturing all that. Okay, collection of important data. The GC logs, right? We need the GC logs. And how do the GC logs help us? They help you, help provide you just directly, just in the GC logs itself. You have the pass times, you have the GC frequency, the type of GC, young, mixed, whatnot, the heap utilization, Chelsea, Eden, occupancy before, occupancy after, etc. And then you can plot the heap utilization. You can calculate the real response time stats. You can identify contributors, like say mixed GC was the contributor, or the last mixed GC, the last of the four mixed GCs was the contributor to the worst case pass time. So yeah, so you can look at that and you can identify all these things. You can calculate your GC overhead and look at your pass distribution. You can feed it to GC, you have to write a parser script, feed it to GC histo, JFree chart, what you have it. What else do you need? G1 is new. You need a baseline configuration that you have used in the past. And we understand that. We know G1 is new, and we know that your past configurations were highly tuned, right? And that's fine. Don't worry about that. But you need to understand, you need that for comparison, and we need that for comparison because we would want to know what works. You want to know what works, what has worked in the past, what doesn't work in the past. Why do you need G1? You have to ask that question to yourself. And then comparisons will help you and us come with a baseline configuration for G1, and then an experiment plan. We'll go this direction, or if that works, then experiment A, B, C, and so on and so forth. What else? What other data do you need? You need the application statistics. You need the response time, not just the ARG. Remember, we spoke about that earlier. Footprint, throughput metric, your CPU utilization, and other CPU-related statistics. Our advice to you is investigate any unexpected behavior. Check your configuration. More often than not, it's operator error. It's happened. Sometimes you bring a stale command line option with you, and you don't remember what happened, why you used it. You just remember it worked. It gave you some 5% benefit. You carry it forward to G1, probably messes up everything. It's happened. I look at logs every day, so I know. Okay, so I'm going to dive into G1 GC analysis. We have 25 minutes, so I may go a little faster with what I'm going to show you next. So Charlie has already covered this, most of it in his section, and we do have this information on the blogs that I was talking about. So I'm just going to talk quickly about the G1 phases. What is a concurrent marking cycle phase? It involves the initial mark, which is piggybacked on a normal young GC. It's stop the world because it's piggybacked onto the young GC. Marks the routes. Then comes the route region scanning. It runs while the application continues to run. It must complete. You have to scan all your routes, the references into the old generation. You have to scan that before the next GC can happen. Concurrent marking. It finds reachable live objects over the entire heap. It runs while the application is running. It can be interrupted by a young GC. Remark. It stopped the world. Charlie already mentioned that. He mentioned about the SATB, the snapshot at the beginning stuff, and then reference processing. It is a part of remark. Cleanup, which is partly stop the world and partly concurrent. What is stop the world? The liveness accounting, identifying the completed free regions are stop the world. Remembered set scrubbing, cleaning up of that is stop the world. And then resetting the empty regions and returning them to the free lists are concurrent part of the cleanup cycle. What's the evacuation pause in G1? It's the copying pause. It's both young and mixed GC. They're both stop-the-world events, GC-induced pause. If it's a young collection, copies all live objects into the in young regions into the available unused regions. If it's a mixed GC event, it copies all live objects in young regions into new regions and some old, because now it has the markings. Remember, a mixed GC cannot happen until you have the marking information. So now you have the marking information, so you know what old regions you can collect, what live objects you can move, right, from the old regions. So you move them into unused regions. What diagnostic flags can you use? You can use verbose GC, which is similar to print GC. The output looks like that. You can use print GC timestamp, which prefixes the elapsed time since the start of the JVM process. Output looks like that. Print GC date stamps, again, adds time of day prefix to it. Looks just like that. Diagnostic flags again. This is what I use. I use print GC details and I use print GC timestamps. What does print GC tell you? And I'll show you. I'll walk through the. One thing you need to know about G1 logs, it gives you a lot of information. And it's because it wants to be transparent. It wants you to understand where are we spending those times, right? So if something is like really out of the ordinary, you know exactly, oh, look, I'm clearing my card table and it's taking too much time. Something like that, right? So it gives you all that information. It gives you whatever I've said over there, and I'm not going to read that, and just going to move on very quickly. Also, it shows you the Eden survivors, just like you would see in parallel GC and CMS. It's much more readable, though. It shows you the occupancy before, the total size of Eden. After the collection, Eden is, of course, 0. What is the total size of predicted Eden? So the predicted size is less in this case. Survivors were 0 before. Now you have 104 meg that survived. And then the total heap. It's much more readable. I like it. Okay, understanding the logs. This is how a log looks. It's a big log, so I'm gonna take it part by part and piece by piece, and then I'm gonna talk about it very quickly. Parallel time. It's the overall elapsed time of the main parallel part of the pause. So you see, this was a young pause. It tells you right on the first line. The parallel time is right there, and then it starts. So these logs are basically ordered on thread ID, the GC thread ID, and are consistent on each entry. So whenever you see them, you will see that the same thread ID corresponds to the next entry, all from the worker start to whatever next, right? So the first entry you will see the worker start, which is a timestamp at which the GC workers started. And it shows you average, min, max, difference. This is 7 update 4 format of the log. So it'll tell you how much on average and whatnot. So the next entry you would see, let me just make sure I didn't skip through anything. Okay. The next entry you would see route scanning. Remember I defined that earlier. So it's a time taken to scan the external routes. For example, it's a system dictionary that points into the heap. And it shows per thread. It corresponds to the previous entry of the thread, and then it has average, min, max, and difference. Update RS is update remembered set. Any buffers that are completed but have not yet been processed by the concurrent refinement thread before the start of the pause have to be updated, right? So the time depends on the density. So it's a coarse or fine or whatever. So it depends on the density. If it's coarser, guess what? It'll take more time to update those remembered sets. So yeah, that's what it says here. And then the number of process buffers are right there. I don't know if I can use a mouse right there. Yay, right there. Scan RS. So we updated the RS, scanning the remembered set, looking for pointers that point into the collection set. Again, average, min, max, difference. Object copy times, again, so this is the object copy time, which is what you would see in a young collection, right? The copying time in the young collection pause. So this is what corresponds to that, remember. So object copy time is the time that each individual thread spent copying and evacuating. Again, it's average, min, max, difference. Termination. So what is termination time? What do you mean by termination time and termination? Basically, when a worker thread gets done with its work, so it's done scanning and copying objects and whatnot, it enters something called a termination protocol. So in that protocol, after it enters the protocol, it looks for work to steal from others. And if it does get the work, and once it finishes the work, guess what? It again enters the protocol, and again looks for stealing work and stuff like that. So the number of attempts that it tries to steal work, that's counted in the termination attempts. So that's another thing to look for. If you have more time, so just more number of counts for one thread than the other, maybe it's not balanced for some reason. So again, it has average, min, max, difference. And then finally, we have, in the parallel phase, we have the worker end, which is again timestamped, individual GC worker stops, and then the worker time total, the time taken by individual GC worker. Again, average, min, max, difference. And then there's something called GC worker other. So basically, it just means just what it says. It's the time that cannot be attributed to whatever I mentioned earlier. So it should be quite low. So again, if it's high, and we've seen cases where it was high, and it was because it was increasing the code cache occupancy because of when tiered compilation was enabled. So it was not a part of G1. It was basically a bottleneck in the JVM itself. So this was high. Clear card table, time taken to clear the card table of RSET scanning metadata. Other time taken for various other sequential GC phases. Choosing C sets, so you want to finalize the set of collection sets, the set of regions to collect, basically. It should be usually very small. And if you have old regions in the mixed GCs, basically if you have marking information already available, guess what? It may take slightly longer because now you have old regions to collect as well. Reference processing, time spent in processing references. Reference enqueuing, trying to place them on the pending list. Freeing CSAT, time spent in freeing the set of regions that have just been collected. You just collected a bunch of regions. Guess what? You need to free CSATs, including the remembered sets of the CSATs. Now, there's a diagnostic flag that's called print adaptive size policy. What it does is, so first thing to note, we do not support adaptive size policy, the flag itself. It's only supported for parallel GC. But we do use that flag to find out ergonomic information right here, as you can see. It shows you the pause was doing CSET construction. It starts choosing CSETs right there. It predicts a base time, and it knows because the target pause time was 200 milliseconds, so the remaining time is still 155. So then it's another calculations. It adds young regions to it, Eden sizes, survivor sizes, and now the new predicted time is 138 because it knows we have 200 milliseconds, and guess what? We were really quick, so we have enough time to add more regions or whatever, do more work, basically. Choosing the collection sets and stuff like that. So it's very useful information, at least for me. I understand where things go wrong. I can look at that and figure it out. So post 7U4. So I know 7U4 had these amazing logs, but sometimes it's too much information. So what we decided is that people who don't want that much information can actually go choose what they want. So you can choose fine, finer, finest. Fine is similar to print GC, but now it has a cause. So for example, that first one was a young GC with initial mark, and it has G1 humongous allocation for that. Then the next one was evacuation pause, so that's a cause of the GC, right? Finer is similar to print GC, but this time we don't have the individual thread times. You just have, say for example, root scanning happened, and what was the average, min, max, and difference. So not those individual threads, remember? And the finest is exactly what I just told you about. It has all the information that you need, so have at it. Before I go into the tuning knobs, I want to talk about evacuation failure, because we all need to know that. What is an evacuation failure? It's a promotion failure that happens when you run out of heap regions. So it can happen for both, or survivors or promoted objects. Heap cannot expand. It's already at its max. And how do you know you are having evacuation failures? You look at your log, and it shows by this indicator 2 space overflow. It's very expensive. GC still has to continue. You just can't say, oh gosh, I don't know what to do. So it has to continue. It has to, whatever objects were unsuccessfully copied, they have to be tenured in place. Any updates to R set of the regions in the C set have to be regenerated. How do you avoid it? So increase the heap. We have something called the G1 reserve percent, which is 10, defaults to 10. Basically, it's the reserve memory for in case you need more two space. So right there, if you have a evacuation failure because of two space overflow or whatever, try to increase that. Start the marking cycle early. Increase the number of marking threads. You can use something called concurrent GC threads right there to increase the number of marking threads. All right, moving to tuning knobs. So I'm going to talk about initiating marking cycle and taming mixed GCs. And these are the three knobs that you need to learn. One is called the initiating heap occupancy percent. It defaults to 45. It's the occupancy percentage of the entire Java heap. Again, difference from CMS, it's not just the old generation. It's the entire Java heap that triggers a marking cycle. There's something called G1 old CSET region live threshold percent, which is actually when do you consider a region to be a good candidate for inclusion in a mixed GC? So it tries to look at the threshold percent of how much live occupancy is for that region, and it tries to include that. The default is 90. So if you have 90% of live data in your old regions, guess what? It will be included, 90% or less. G1 mixed GC count target, it defaults to 4. That is the maximum number of mixed GCs that will happen after a marking cycle. So let's go with the first one, initiating heap occupancy percent. So how do you tune it? Like I said, the default is 45% of the total heap occupancy. So what do? You observe at what old gen occupancy initial mark phases begin. You don't want the marking cycle to start. It's similar to what we do for CMS, right? You don't want a marking cycle to start too early or too late. You will either spin or you'll have a two-space overflow, which eventually will lead to a full GC, which is single-threaded, like Charlie pointed out earlier. Observe how much is reclaimed by viewing heap occupancy at initial mark and after marking and mixed GCs. You want a reasonable amount of object reclamation. Very tricky. Okay, so if you observe that your maximum heap that you're utilizing is below your actual maximum heap that you specified, and you have that room, and you want the GC to use that. You don't have anything else in mind for that particular the space. I will show an example. And if you want to use that, guess what? You can set your initiating heap occupancy percent higher to push that maximum heap utilized occupancy higher, right? That's what it means. But be careful not to set it too high. Guess what? You set it too high, then you end up with a two-space overflow. So on the example that I'm going to show on the next slide, what we did is that we asked them to increase the initiating heap occupancy percent to 70 to reduce throughput and reduce the concurrent overhead. Right here. So what happens when we asked them to increase that? So they were working with a 3.2 gigs almost of heap, and the default value of 45 was what it would do. It would start a marking cycle earlier. So when the heap occupancy would be 1.4 gigs or so, it would start a marking cycle. And now we have this much room that we're not using. The marking cycle starts, it does everything, and comes down. So we're doing more mixed GCs, and they're expensive. So we asked them to raise it to 70, and look at the difference. So again, the turquoise color is mixed GC, the red is young GC, and stuff like that. Old CSET live threshold percent. We'll talk about that next. So I'm going to show you some GC pause distribution. The graph on the top that I'm going to show you next is basically generated when we dropped the CSET live. So remember, CSET live threshold percent defaults to 90. We asked the people to drop it to 65, and the graph below is expanded to match the scale, like this. So you see that? It directly, so you see how it shifted, the pause distribution shifted? I know you cannot tell the numbers, so I have written it down here, so, because I cannot tell it clearly either. On the bottom, you will see it ranging from 250 milliseconds to 325 or a little over 325 milliseconds. On the top, we said only include live threshold regions that have live threshold, don't cross the threshold of 65, basically. The distribution moved into 160 milliseconds to 235 milliseconds range. So this area is what moved over here. So so our pause times got reduced drastically because we did not include as many live, more expensive. We kind of reduced the expense of the regions, basically. The next one is G1 mixed GC count target. I have 8 minutes. So what you need to do is you need to first check your GC pauses and see are the defaults working for you. In this case, the default for G1 mixed GC count target was 4, which did not turn out to be optimal. So what happens is that we're trying to collect basically by default of 4, we're trying to collect 1/4 of the old regions at every mixed GC collection, right? And that could give us a very large collection set. So look at that. So again, the red is young collection times, which is almost averaging to 200 or less. The default is 200. And then those turquoise colors are mixed GCs. And you see how over time, so I'm going to start here, right here, and then it goes higher, and then it goes higher, and then it goes higher. And see how the last collection is so expensive, right? It's taking about 850 or more milliseconds just for the last one. So you see, number 1, number 2, number 3, and number 4. And that's what our maximum was, number 4. So what we told them is increase your mixed GC count target. And another thing we could have asked them to try was to work with the GC heap waste person. Yes, Dave, that is exactly how it looks. It's like questioning. So we asked, another thing we could have tried was to ask them to increase the G1 heap waste percent. Basically, G1 will revert back to young GCs if the amount of space reclaimed is less than that value. So we're saying that we're okay with 5% heap waste. But if you say increase it to 10%, so we're saying, oh, well, we're okay with 10% waste, so just go back to young GC earlier. So that could have also helped them. All right, so this probably is the last one that I'm going to cover. And I wanted to mention this because the defaults clearly were not working in this case. So this application had 36 gigs of your heap size. And because of that, remember G1 defaults its nursery to 20% of the heap size, which in this case was 7.2 gigs. The object allocation rate and the liveness of was such that G1 was not able to meet its pause time target goal, which was set to 350 milliseconds. So our recommendation, guess what, was simple. Drop your minimum nursery size. And I'll show you why. Look at that. So the first young collection itself took more than 1 second. And you can see, and then I also plotted that's how I got to know what was a problem. I plotted it over here. This is JFree chart. This is GC histo. So the JFree chart shows you that the Eden starts at little around 7.2 gigs. So the first collection itself was getting expensive. So there was no way that they would, because of the way the application was, that they were going to meet their pause time goal. So we asked them to drop it lower to this somewhere here, and the minimum nursery. And guess what? They were able to meet their pause time goal with that. We have 5 minutes. These are the aliases that I would like everybody to at least monitor and then start using. Ask questions and you'll get answers. And this was the weblog that I was talking about, Poonam's weblog.
Very good. So we have about 5 minutes for questions, but before we do that, I'm going to kick off a little bit. I'll kick this little section off with a little funny story about G1. So it took quite a while for HotSpot to support G1. I'll share with you a funny little story or a joke that has gone around inside of HotSpot as to why that occurred. So you heard us use this term evacuation. What we were seeing for quite a long time is we saw that it was evacuating before spaces or regions were full. We promptly called that the premature evacuation. So G1 in its adolescence days had a little problem. Hopefully this isn't the one thing that you remember from this talk today. Okay, so go ahead with your questions. Go ahead.
What tool or tools would you recommend for analyzing these logs?
That's a very good question, tooling for G1. So what I've used and what Monica tends to use is a combination of two things. One of them is GC Histo, which you kind of have to do a little finagling here. So when GC Histo currently supports CMS and parallel GC. It also turns out that GC Histo has a mode called simple log format. So what you end up doing is you write a little parser in Perl or awk, something of that nature, and you have space delimited fields, and that you load that inside of GC Histo, and then you see this distribution of pause times. The other critical piece with understanding and seeing how G1 is behaving and driving your analysis efforts is having something that can plot the heap occupancies and the actual sizes of the young generations and old generations. What we did is somewhat similar in that case. So we developed something that is based on JFreeChart. We parse the logs that pulls out this data of heap occupancies, and then we also, use as a x-axis, we use time. So we can see what these heap occupancies are doing at a given time, and then we also lay over top of that the pause times. So those are the two things. The unfortunate thing is there isn't at least I haven't seen a really good off-the-shelf tool just yet that can do this. That's always was one of my main motivations, is to drive this tooling side of it, because that's always one of the big challenges. It's a very common engineering problem. You put out this great technology, but then you always have to ask this question, where's the tools? You got something there, Kurt? What is that one of your tools?
Yes.
Okay.
That's good.
So talk to Kirk afterwards if you're interested in tools. Yes?
How does it calculate the threads? Dynamically figures out how many threads to use based on the scores.
The number of GC threads?
Yes. How is that done? The seed is a value, a large number of scores. I don't think it's small.
There's been some changes that have been made to that. I don't recall the update releases. I don't know if, Monica, you remember the exact formula, but I think it's based on the number of underlying hardware threads, and I think when you exceed a certain number, it takes 5/8 of that number. This is one of the things maybe to keep in mind if you're running multiple JVM instances, that you may end up tuning the number of GC threads.
It's actually 5/16 now, I think.
Is it 5/16 now? Okay. Other questions, Kirk?
Everything seems to be focused on pause time. Does some of the calculations actually take into account the concurrent time? Because that's still stealing CPU away from your application.
That's a good question. That's all part of the prediction model. So the question is, and thanks for asking me to repeat that. So the question is basically, a lot of the focus with G1 is on pause time. So does the prediction model that predicts how long a given GC pause is going to take, does that take into account the amount of concurrency that you have? Because when you have the concurrent sort of collection activity going on, you're stealing CPU cycles. And that's all part of this prediction model that G1 uses. To my knowledge, I don't think that it does. There are improvements that are being made through folks in Oracle Labs to help us with better prediction models. Another question.
So I'm wondering if the adaptive sizing, or whatever that's happening in G1, is taking into account survivor space flooding, or have you seen that survivor space flooding actually matters in the G1 collection, given that it's structured?
Okay, so the question is G1 in his prediction model taking into account the notion of overflowing survivors? So Kirk is using the notion of survivor flooding, which I'm interpreting as survivor spaces overflowing, or you get very rapid promotions into old generation.
Well, which we call premature promotion.
Yes.
So does it, okay, so It's really driven by the pause time target. So the lower you set a pause time target, what you expect to see happening is young generation gets sized smaller and smaller to accommodate the young generation pause time. So depending on how long your objects stay live is going to dictate how quickly they get promoted. The thing to keep in mind is the amount of time that it takes to collect an old generation region is essentially about the same as what it's going to take to collect a young generation, assuming the same level of occupancy. There's a few edge cases there to deal with because you have to deal with references into that region, but you can generally think of it that way.
So you're saying that the survivor space flooding doesn't matter that much?
It's not as critical because you have this ability to compact old gen,
Right.
and then because you don't have this. You don't have this huge, expensive cost of doing a compaction, so you don't have to do this full GC. So you now have this ability to do essentially incremental or partial compaction via the mixed GCs.
So the next obvious question is why have survivor space?
That is a good question. It is a good question. I don't know the answer to that. I don't know the answer to that off the top of my head. So the question is, why have a survivor space?
So along the same lines, with CMS, well, the worst case scenario is indeed defragmented stuff. And so it has been shown in the slides or mentioned 1 or 2 times the word worst case scenario. Can you comment on what possible
What are the sort of things that lead to the worst case scenarios?
So I don't know. So is that this partial defragmentation just a word or something? I don't know.
Some of the biggest challenges, I would say, for G1, and in particular with an application, so if you start from the simple standpoint and move to something that's a more complex sort of situation, and probably less likely. So the most common situation and challenge you'd probably have with G1 is you start this concurrent marking cycle too late, or it starts too late and you don't have enough headroom and you run out of space. And you have what's called a two-space overflow. Two-space overflow basically means you're trying to evacuate some region or sets of regions to some unoccupied or some other region, and the two space that you're copying to runs out of space. And that's what's called a two-space overflow. That, in order to recover from that, you have to do a full GC, and then you have to undo a bunch of this accounting stuff with references that you're keeping to recover from it.
With CMS, if things go wrong, they go really seriously wrong, and maybe here it's a little bit more limited. They're going seriously wrong.
The circumstances, or the number of circumstances, and I'd say the probability that something bad occurs is much less likely with G1 than it is with CMS. We're being screamed at being out of time. Thank you, everybody, for coming. I hope you've learned at least one thing out of this today.